Okay, so I think we can start now. So it's my pleasure to introduce you Lorenzo Posti, who is currently a postdoctorant at the University of Strasbourg, working with the team of Benoît Famer, Rodrigo Ibata. And so Lorenzo was defending his PhD in Bologna in 2015, and then he moved in Groningen for 3 years. I mean, he moved just before the COVID in Strasbourg in 2019, and today is going to present us where the feedback fails and the clues from dynamic to massive galaxies. So the floor is yours, Lorenzo.
Okay, so thanks a lot, Guillaume, and thanks for the invitation. It's a pleasure to be able to tell you a bit about what we did in collaboration with these people that you see listed over here. Obviously, it's a pity not to be able to be there in present, but you know, we have to make do with the best that we can in these strange periods. So yeah, what I wanted to tell you today is a bit about what we learned in terms of galaxy evolution, and in particular on the role of feedback in galaxy evolution by studying the dynamics of especially massive galaxies. So in general, I'm interested in galaxy evolution, and to me, understanding galaxy evolution, at least to first order, means understanding the connection, the deep and intimate connection that is there between galaxies and dark matter halos, at least in our lambda CDM cosmological universe. And this connection is important because this is really the backbone that sustains all of galaxy formation in this cosmological context. So understanding this connection means understanding to first order galaxy evolution. And the connection of galaxies and halos is basically characterized by all of the properties of the population of dark matter halos, such as their mass, their concentration, their spin, or their formation time. How do all of these things relate to the properties that we can observe for galaxies today, such as their mass, their colors, their angular momentum, but also their morphology, and etc. And so all of these properties that you see for dark matters on the left are linked somehow to the properties of the galaxy that we observe today on the right. And understanding really this connection gives us, allows us to unveil galaxy evolution, at least to first order. So arguably the most important link of all of this connection is the link between the galaxy mass and the halo mass. And this is because mass is known to be probably the most important properties that drives galaxy evolution. And so in this talk, I'm going to focus on this connection between galaxy mass and halo mass. So fortunately, we know already a lot about this connection. And so I'm going to start from what it is already known today, and then I'm going to develop this a bit through the rest of the presentation. And we know, for instance, today that galaxies are rather inefficient systems at forming stars. And this inefficiency becomes immediately apparent as soon as you look at the stellar mass function of galaxies, which means that you take a portion of the universe, then you count how many galaxies are there in a given stellar mass bin, and you end up with a function that looks something like this. And then you can compare this with a similar mass function, but for dark matter halos. And this is something that obviously you cannot observe, but it is derived from theory. So these curves are very different from one another. They are very discrepant, and the discrepancy becomes larger at lower masses and at higher masses. And this discrepancy already tells us that galaxies are rather inefficient at converting all of the baryons that are within the halos into stars. And they become less and less efficient going to lower masses, but also going to higher masses. And the standard interpretation of this inefficiency is basically, we think that this is due to two different physical processes that act on different scales, on low mass and high mass scales. At low masses, we think that the inefficiency of galaxies, forming stars of galaxies, is due to the feedback coming from the stars that are forming into the galaxies. So the stars form, they explode as supernovae, they inject energy back into the interstellar medium, and this impedes star formation. This contrasts the formation of new stars, and this is the reason why galaxies are rather inefficient, especially low mass systems where the potential wells become shallower, and so it is more difficult for them to retain the winds that the supernovae are injecting into the interstellar medium. At higher masses, instead, we think that there must be another more energetic phenomenon that is happening in order to drive the sharp drop-off of the stellar mass function. And this is often interpreted to be an effect, a consequence of the feedback from the central accreting supermassive black hole, that is the AGN. There is accreting material, and then it is injecting energy back into the interstellar medium in forms of outflows or jets or very, very powerful energetic ejecta that are impeding the formation, the cooling, and the inflow of new gas into the galaxy. And so this discrepancy between these two curves, the stellar mass function and halo mass function, does not only tell us about feedback in galaxies, but it also tells us about the connection between galaxies and halos. And this is immediately apparent when you look at when you compare these two curves horizontally in this diagram. So you do it like this, which means comparing the abundances of objects in the universe, comparing the abundances of dark matter halos and galaxies at a fixed number density. And so when you do this, you can immediately obtain a relation, an average relation between the mass in stars and the mass in dark matter in a galaxy. And this is something that I'm sure everybody has already seen. This is a plot that I've taken from a recent review in the field that shows you the determination of the stellar to halo mass relation in galaxies in the form of stellar mass, of the ratio of stellar mass divided by halo mass as a function of halo mass. And so, as you can see, each of these curves is derived from a different group using, in principle, different techniques and different data. And they all agree, they all have this huge consensus on the form of this relation, on the shape of this relation. That is, this ratio, stellar mass over halo mass, increases with mass up to a peak, which happens at around the mass of the Milky Way. And then this ratio decreases again with halo mass in this case. And this is again due to this very characteristic particular behavior is due to these two physical processes. At low masses, these things drop down because of stellar feedback, and at high masses, we interpreted that the drop at high masses is due to feedback from AGN somehow. And so this relation is very important because this is giving us a very clear-cut dynamical prediction. That is, the relation between the mass in a galaxy, the stellar mass in a galaxy, and the dynamical mass in a galaxy has to be very highly nonlinear. As you can see, there is a very pronounced bend. There is a very pronounced characteristic at around the mass of the Milky Way that we should be able to see by testing, by probing the kinematics of galaxies. And so this is what I want to do, and what I want to show you for the rest of the presentation. It kind of tests to see if we can detect really this high nonlinearity that we expect it to be in studies of dynamics of galaxies. And so this is the outline of the presentation, and I already give you the main takeaway that I'm going to tell you at the end of the talk. That is, this relation, the stellar to halo mass relation, has a huge dependency on galaxy type. So we will see that there is no linearity in the stellar mass dynamical mass relation, depends a lot on which type of galaxies you're looking at. So after having introduced the sample that I'm going to be using, I'm going to go through two lines of evidence for this very huge dependence on galaxy type. The first one comes directly from the scaling relation of these galaxies. So these relations immediately tell us that there is some dependency on galaxy type in this relation to be expected. And then I'm going to be going through direct measurements of the halo masses of both these galaxies from H1 rotation curves, and for elliptical galaxies from the kinematics of their globular clusters, that would be telling us precisely how much of a difference there is for galaxies of similar stellar mass. And then I'm going to conclude with some comparisons to simulations. So the sample that I'm going to be using for most of the presentation, at least, comes from the catalog that was collected recently by Federico Lelli and collaborator, that is called SPARC. So this comprises 175 nearby spiral galaxies that have two characteristics. They have been observed with Spitzer at 3.6 micron photometry, so they have infrared, very accurate and good infrared images from space. And this is very important because we can get a measurement of their stellar mass and their distribution of the stellar mass distribution within the galaxies very accurately, because it is in the infrared. And then all of these galaxies have also very accurate rotation curves that come from radio interferometric data. And this is very important in order to get the dynamical mass of these galaxies. And so you see that this sample is very nice, because we can have a very good handle on the stellar mass and on the dynamical mass of galaxies for the same systems. So the sample is not complete, obviously, but it is fairly large, and it is spanning a very huge range, at least in stellar masses. So it goes from tiny dwarfs in the local group to giant disks at larger distances. And so let's start to understand what, to dig a bit more into the relation between stellar mass and halo mass in these systems. And we start from the scaling relations of these galaxies. So we all know that at least spiral galaxies follow some very nicely well-defined scaling laws. And in particular, arguably the most important scaling relation, at least dynamical scaling relation for these galaxies, is the Tully-Fisher relation between the stellar mass and the velocity along the flat part of the rotation curves, which traces the dark matter. And this is known to be a fairly tight and linear correlation along about 5 orders of magnitude in stellar mass. And this is actually how the Tully-Fisher relation looks like for the sample of Spark that I just introduced. Now, this is not the only dynamical scaling relation that looks like a simple and tight power law across 5 orders of magnitude, but also, for instance, the relation between stellar mass and stellar specific angular momentum, which I'm calling the Fall relation after major contributions from Mike Fall in this field. This is also a very tight, observationally, we can measure this to be a very tight and linear relation across 5 orders of magnitude. And also, if you look at simply the mass sizes of disks, just of disk galaxies in the nearby universe, this also looks like a fairly linear relation across at least this, this sample that I'm using here. Now, this is important because we see that we have this very important dynamical scaling relation that involves somehow the stellar mass and the dynamical mass of galaxies that do not show any bend, do not show any particular feature. They all look like simple power laws. So it is natural to ask if this is compatible at all with having, a high nonlinearity in these galaxies, in the relation between stellar mass and dynamical mass, so stellar mass and halo mass in these systems. So in order to answer this question, we need to go back to where do the scaling laws originate for galaxies. And so we need to go back to dark matter for a minute. So we know that dark matter halos themselves are objects that follow some tight and well-defined scaling relations. And for instance, the mass of dark matter halo is proportional to the power 3 of their radius, but also to the power 3 of their virial velocity. And since these halos in lambda CDM are not spherical and they do not live in isolation, the nearby halos exert torques onto each halo, and then the result of this process is that the dark matter halo starts spinning a bit, and so they acquire some angular momentum from the interaction with the nearby surrounding halos, and they do so in a way that that the mass of the halo also correlates with the specific angular momentum of the dark matter halo as a simple power law, as you can see here. So this is the starting point, right? We have dark matter in our universe, and the dark matter halos are filled with gas, and then we need to form stars in this, right? Because we're interested into the galaxies, we observe the galaxies, and so we need to form stars within the halos. And so to do this, I'm going to be, simply parameterizing very simply galaxy formation in this context, right? Just by using this very very simple three free parameters that are just the ratios of mass of the stars to the dark matter, of angular momentum in the stars to angular momentum to the dark matter, and the ratio of the velocity at which the stars are rotating in the galaxy to the characteristic velocity, the variable velocity of the halo. And this is very useful because these simple parameters allow me to take the observed scaling relations for galaxies and to reference them to the very well-known scaling relations for dark matter, right? We know that gravity, the gravitational clustering of dark matter, hierarchical clustering, is makes objects that have power laws, that have scaling relations that are of this form over here. So we can use this knowledge, and we can use these simple scaling relations for dark matter as a reference for the observed scaling relations for the galaxies, and use these parameters basically to incorporate all of the complex physics that goes into galaxy formation, so into the hydrodynamical processes that actually form galaxies. And so using these three ratios, we can immediately rewrite equations for the scaling relations of galaxies by using, starting from the ones from dark matter. And so you can see that we have an equation for the mass size, for the Tully-Fisher, and for the relation, for the mass angular momentum relation. And as you can see, all of these equations have a basis of a power law, right? V is proportional to m star to the power 1/3, but then this dependency is modified by the introduction of this ratio, Fv and Fm in this case, that in principle are themselves function of mass, and so they can modify the shape, the behavior of these scaling relations, at will, right? Depending on how these fractions depend on mass. And so the idea is now really to use the observations and use these equations to infer some constraints on these fractions. And since these fractions hide all of the complexity of galaxy formation, then we can really hope to learn something on galaxy formation by looking at, what do the observations actually tell us about how these fractions should vary as a function of mass. And immediately, when you start doing this, you immediately realize that we can input some of the knowledge that we have already, right? Because the ratio of masses, of stellar mass to halo mass, is something that we kind of already know, right? We have already studies for instance, from abundance matching, right? That are the simple process that I described before, that allows us to derive the stellar to halo mass relation that has this characteristic shape that we saw before. So we can kind of input this knowledge into these equations and see what are the expectations in the scaling laws for galaxies, and see how do they compare to the observations. So if we do this, if we input this functional form for Fm, and we keep the other fractions Fj and Fv constant, just for simplicity for the moment, we immediately see that we cannot reproduce the observed scaling relations. And the reason is very simple, right? The predictions that we have from this are these thick black curves. And as you can see, they are off of the data basically everywhere. And the reason why they are off is that inputting the knowledge from the stellar to halo mass, the non-linearity of the stellar to halo mass relation, makes it such that the scaling laws expect a break. They should break at around the mass of the Milky Way, and it doesn't look like they do so from the observations, at least. So in doing what we did, there must be some problems, right? There must be something that is not accurate. There is not an accurate description of the reality, and so it might be at least one of these two. The solution to this conundrum must be at least one of these two possibilities. One is that the ratio of stellar mass of halo mass for disk galaxies is not compatible with the one that we derived from abundance matching, right? So it doesn't have the characteristic non-linearity that I showed, and this would make the other two fractions to be constant with no problem. Or another way to solve the issue is that, yes, the stellar to halo mass ratio must come from abundance matching, but then also the other two fractions that I left constant in for these expectations for these plots over here, then also these things must not be constant in order to have linear scaling relations that we see here. And so we can build models according to these two hypotheses, and we can ask, what do the data prefer? And doing this kind of things is interesting because these two solutions have also very different physical meaning, right? So here in the plots here, you see the scaling relation. So this would be the Talley-Fisher, the mass size, and the 4 relation. In left is basically left column would be one of the two hypotheses, and the right column would be the other one. And these two hypotheses are very different physically, because if we keep the stellar to halo mass ratio from abundance matching, then we are kind of already saying that the feedback must be very efficient at quenching star formation at the high mass end. In particular, we want the stellar to halo mass relation to bend, to have a characteristic turnover at masses above the mass of the Milky Way as a consequence of feedback, probably. And so if feedback is doing this, it is suppressing star formation, then it is also possible to think that the same feedback is redistributing mass around galaxies, baryonic mass around galaxies, because it has huge outflows. And also it is transporting angular momentum around. And so it is possible to think that these ratios would not be constant in a situation in which feedback is doing, is having a huge role in galaxy evolution at the high mass end. On the contrary, in models on the right, where you have the stellar to halo mass relation that does not break, that does not turn over, as abundance matching would suggest, then you could imagine that feedback is inefficient, right? It's not really turning down the stellar to halo mass relation. And so maybe it is not suppressing star formation very efficiently at those masses, and so it is not transporting angular momentum, and it is not redistributing baryonic mass around, and so also these two fractions could be constant. And obviously, both models can reproduce the scaling relations. Both hypotheses do have decent fits to the scaling relation. This is kind of by construction, but they do it in a very different way because they have very different predictions for what these ratios should be, how do these ratios should vary as a function of mass. And as you can see, in the models on the right, if we impose our knowledge on the stellar to halo mass relation that comes from abundance matching, then also the ratio of velocities and the ratio of angular momentum should have similar bends, should have similar turnovers at around the mass of the Milky Way. So this would mean that a galaxy that is at 10 to the 11 or so solar masses in stars should have retained about a tenth of the angular momentum that the dark matter halo has, as opposed to the Milky Way, which would have retained the entirety, 100% of the angular momentum that the dark matter halo has. This does not happen in the models on the left, in which you allow the stellar to halo mass ratio to grow as a function of mass indefinitely, and so the other two ratios can be constant. And from a statistical analysis, you immediately realize that if you want to fit scaling relations that are linear, you have no statistical need of inducing breaks anywhere, of inducing a turnover anywhere. And so the models on the left, the models that are linear, would be statistically preferred just because they are, more simple, they have less free parameters. So if this is the case, if actually the models on the left are preferred, then this tells us something very, very interesting, right? This tells us that the stellar to halo mass relation for these galaxies is very different from what we expect, does not turn over at high masses, and so the ratio stellar mass of halo mass continues to grow linearly. Now, is this something that we can also see, that we can also probe more directly by looking at by measuring halo masses in these galaxies? Well, this is what we try to do, and fortunately, these galaxies have the very nice properties of having very large, typically have very large extended H1 disks. And if you can observe these H1 disks that extend out to a significant fraction of the virial radius and much larger than the optical radii of galaxies, this is very nice because you have a direct probe, a direct tracer of their gravitational potential, because H1 is tracing cold gas. And this probe of the gravitational potential extends out to typically 50 kpc or even 100 kpc in some of the most massive disks. And so you can really probe directly the gravitational potential out to, a significant fraction of the virial radius, which allows you to determine the halo mass very well. And so what we did is something that people have been doing since the 60s, so it is really nothing new, which is that we modeled the rotation curves of disk galaxies, and we decomposed them into the massive components that we know are actually present in galaxies, so in stars, in gas, and dark matter. So what we did is we took observations of radio interferometric observations of the H1 disks in these systems. And these observations gives us the rotation curve, so the rotational velocity as a function of radius, as you can see from the black points in this diagram over here. And then just by integrating Poisson's equations on the surface density of gas that you can immediately derive from the H1 flux, we also can obtain the contribution to the circular velocity that is given by the gas, which in most cases, at least at the high mass end, is negligible. Then we can do the same thing for the stars. So we can take the infrared photometry, we measure the surface brightness profile, and with this we integrate Poisson's equations, and we have the stellar the contribution to the gravitational potential coming from the stars, and this will give us the yellow curve that you see over here, which I call V star in this equation. And this is obviously, this can be shifted up and down according to the mass flight ratio that you assume for the stellar population that you're looking at. And so it can be a bit higher or a bit lower, depending on what M over L you assume. And then everything that you're left with is obviously given by dark matter in this context. And so the obvious thing that you can do is just assume a halo profile, which in this case is a standard Navarro-Franken-White profile that has two free parameters, halo mass and a concentration. And so you can fit the rotation curves for these two free parameters, adding a third free parameter, which would be the stellar mass flight ratio. And you can ask, you can explore what is the best model, you can explore their uncertainties. And basically, we need to include also the mass flight ratio as a free parameter, just so that it can shift upwards or downwards the yellow curve that we can see over here. And so this is something that it is relatively easy to do, and we can do it for a large number of galaxies in the nearby universe. And the only thing that needs to be specified is that we need to impose a prior, typically on the concentration mass relation that comes from numerical simulations of in lambda CDM context. And this is just because this, as you can imagine, in doing these fits, there are some degeneracies. And in order to break some of these degeneracies, we need to impose at least a prior knowledge on the relation that is there between concentration and mass. And this is something relatively standard, which we can do. And so we can perform all of these fits for all the galaxies in the spark sample. There are 175 nearby disks. And we can really start now putting individual points, so probing the stellar to halo mass relation really with individual points. And so what we do here is we are showing the ratio again of stellar mass over halo mass, this time as a function of stellar mass. And I'm normalizing this to the cosmic baryon fraction. So this is the black line is the expectation that we have from abundance matching. And these are the points that we can derive with the rotation curves, with the halo masses estimated from rotation curves. So there are a number of things that you can see from this plot. First of all, you see that galaxies are relatively low masses, so below 10 to the 9.5, I would say. They tend to have very large error bars. And the reason for this is that these galaxies are relatively small. And so also the H1 disks are relatively small as well. And so they don't reach as far out into the halo in order to allow me to break the degeneracy the degeneracies in the, in determining the halo mass properly, since the tracer, the dynamical tracer that I have does not extend simply far out enough. And so this is why the error bars in these systems tend to be quite large. This does not happen at a high mass, however, because at high masses, the H1 disks extend very large radii, typically 50 kpc, but even 100 kpc in some cases. And so I have direct probes of the gravitational potential out to, very dark matter dominated regions. And with those data, I am very, it's very easy to just, given a halo model, it's very easy to determine what the halo mass should be. And so this is why the error bars in the halo mass, so in the N star over M halo of these systems are small. And also obviously the signal to noise of the data for these systems is much larger on average. And then you see that all of these systems, all of the high mass systems at above, stellar masses of larger than 5 times 10 to the 10 or so, they all tend to be significantly discrepant with the expectation that we have from abundance matching. They all tend to lie above. And it is systematic in the sense that all of these galaxies, except probably for one that has very large error bars, they tend to lie above. And this, I think, is a very important and very interesting result that we have, that all of the disks, all of the massive spirals that we see in the local universe, they are similar in masses to Andromeda. The green cross here, the green cross here is Andromeda. All of these disks significantly and systematically deviate from the expectations from abundance matching. So what does this mean? Does this mean that abundance matching is wrong? Well, probably is not an accurate representation of this sample of galaxies here, right? Of the disks that are very massive, like the ones that we're probing. However, at the high mass end, at 10 to the 11, at stellar masses of 10 to the 11 or so, most galaxies are ellipticals. So it is in principle possible that abundance matching is only tracing galaxies that are elliptical at this high mass end, and spirals are systematically deviating from it. So in order to probe if this is actually the case, we need to also have dynamical or individual estimates of halo masses for galaxies that have different morphology, that are ellipticals at those high masses. And we try to do so providing dynamical estimates of halo masses. So how do we do it? And the problem in doing this is that obviously ellipticals and lenticulars do not have H1 disks at those masses, at least, at any mass actually. So we need to rely on some different dynamical tracers. And for this study, we relied on globular clusters. So there are a number of at least high mass ellipticals and lenticulars that are nearby and around which there is a system of globular clusters that are relatively well studied. And in some of them, they are not only well studied photometrically, but they also well studied in spectroscopy, meaning that for at least 25 ellipticals and lenticulars, we have very good measurements of radial velocities of all of these clusters around these systems. So in particular, we took data from the slugs survey, which gives us around 25 high mass ellipticals and lenticulars, for which we have of the order of 50 to 500 confirmed globular clusters with radial velocities. And typically we can get radial velocities of globular clusters out to of the order of seven effective radii for this system. So these are fairly, dynamical tracers that extend out to fairly large radii. Unfortunately, they are not cold, so we cannot model them. We cannot model their dynamics as simply as we did for the H1. So we need to rely on full dynamical modeling in order to extract the dynamics and in order to probe the halo mass of these systems. And so what we did is we constructed some distribution function models. So we took the positions and the radial velocities of these clusters and we fed this data into a full dynamical modeling, a full orbital model of all of these clusters around the ellipticals and lenticulars. And with this, we are able to constrain simultaneously the potential of, so the gravitational potential of the system and the velocity anisotropy of the globular cluster systems, which is, you know, and this is important because there is a huge degeneracy in hot systems, in the dynamics of hot systems between the anisotropy, the velocity anisotropy of the tracers, and the mass, also the gravitational potential. And to, you know, and in order to be comparable with the study that we performed before on the spirals, we try to use this kind of the same assumptions for the gravitational potential as similar as we could with respect to the spirals. So we used a potential that has two massive components, the galaxy and the dark matter halo. The galaxy is modeled from the near-infrared photometric images that we have for all of these systems. So it's basically done in the same way as we did for the spirals. And the halo is, again, taken as a simple Navarro-Franken-White halo with a prior on the concentration mass relation. So we use basically the same inputs, if you want, the same assumptions that we did before in order to be comparable with kind of the result that we have in the end. So the modeling that we do is relatively complicated. I'm not going to go through all of this. I can just tell you that what we did is we can reproduce obviously the radial density profile of the clusters. The data you see in blue, the data, and in black the model everywhere in this diagram. So we can reproduce fairly well the density profile of the clusters, and then this diagram that is called the projected phase space. So is the radial velocity of the cluster as a function of radius, so distance from the center. And so this is actually effectively the space where the fitting is taking place. So we fit effectively the distribution function here. And then we can reproduce also for instance, the profile of the velocity dispersion as a function of radius that we derive from the slugs data. So the important bit is actually this diagram here, is that with this model, we have a pretty good inference on the halo mass and the concentration as well of the gravitational potential, so of the dark matter halo around these galaxies. And we have determinations that are relatively well comparable to the ones that we probed before for spirals, and so we can now put the two samples of galaxies together and see if there are any difference. And as you can see, this is probably one of the first times where you can see individual points in these diagrams in the stellar to halo mass relation of galaxies of very different morphological types, at least at the high mass end. And so you see again the plot of a stellar over halo mass ratio as a function of stellar mass on the left and as a function of halo mass on the right. And as you can see, the blue points are the late types, the spiral galaxies that I was able to probe with H1 rotation curves, and the new points are the red ones that are the ellipticals and lenticulars in slugs, for which we determine the halo mass from globular clusters. And as you can see, there is a clear systematic deviation at a fixed stellar mass of the ellipticals with respect to the spirals, meaning that the spirals always seem to lie above where the ellipticals and lenticulars are. And as a matter of fact, the early types are actually following very well the expectation from abundance matching, which is the gray band that you see in both of these diagrams here. So the situation is that at the high mass end, abundance matching is tracing very well the population of early types, but it is not tracing very well the population of spirals. So we see very well that there is a trend, a correlation with morphology, vertically in this diagram over here at fixed stellar mass, if you want. And when you look at the version of this diagram as a function of halo mass, you also kind of see an hint of a threshold in halo mass above which there are not many disks, but galaxies are only ellipticals. So there seems to be at least an indication, possibly, a halo mass threshold above which the formation of these galaxies is difficult, is complicated. And so how do we interpret all of this? Well, it is not, again, it is not surprising. I think it is not surprising that abundance matching does not provide an accurate description of the most massive disks. And this is because if you match, if you go again at matching the stellar mass function with the halo mass function, at the high mass end, this match is completely dominated by spheroidal galaxies. There are about 90% of galaxies above 10 to the 11. And so it is not surprising then that when you translate this into the stellar to halo mass relation, the ellipticals trace very well well, abundance matching is tracing very well what ellipticals are doing, but it is possible that the spirals are completely overshooting this. And now for speculation, what might be the cause of all of this? Well, if we interpret the sharp drop-off of the stellar mass function as a consequence of AGN feedback, so if we say that ellipticals are quenched mostly because of the effect of AGN feedback, then this might indicate that the spirals at the same similar stellar mass do not have suffered from feedback. So feedback, for some reason, has failed in this system. AGN feedback, at least, has failed in this system, so that they could have a stellar to halo mass ratio that continues to grow linearly, and it does not show any sign of turning over at the high mass end. So I think I'm running out of time, so I will go quickly to some comparisons to simulations. And there is at least one important point that I wanted to show you, and is that so what we did is we asked ourselves, do we see any of these massive spirals in cosmological simulations that have stellar to halo mass ratios that are similar to what we see in the local universe? So what we did is we took the public catalogs of two popular simulations that are Eagle and Illustris TNG. We selected a volume that was similar in the simulation, so around 100 megaparsec, which is kind of similar to the volume that the Spark, that the galaxies in Spark, the Spark catalog is actually probing. So we do expect within this volume to find of the order of 10 high mass disks that have stellar to halo mass ratio that are deviating from abundance matching. So we took these two catalogs and we selected disks. We did them kinematically and morphologically. I'm not going to go into this. But then we looked at if in the simulation we could see any galaxy that was, resembling of the galaxy that we just, of this, high mass spirals that we just observed. So in this plot here, you see stellar mass over halo mass as a function of stellar mass. On one side, there are galaxies from the Eagle simulation, and on the right side, there are galaxies from the TNG 100 simulation. So the high mass disks that we observed are the points in red, and the simulations are the squares, are the gray and colored squares. So in both diagrams, the gray squares are galaxies that are ellipticals, according to our selections, and the colored diagrams are galaxies that are disks in Eagle and disks in TNG. So as you can see already, disks in both of the simulations, disks tend to have a slightly higher stellar to halo mass ratio with respect to the average in both simulations. However, especially in the case of Eagle, the absolute value of the stellar to halo mass ratio does not reach the high values that we measure from the H1 rotation curves. For TNG, the situation is a bit better, but still there seems to be some discrepancy here. So this is, if you want, a global issue in the sense that we are taking the entire stellar mass of a galaxy and we divide it by the entire halo mass of a galaxy. But now that we have the simulation, we can have a look if there is if there is another side of this issue, of this problem, that is more local. And so to explore this possibility, we can select a galaxy, a single galaxy at around 10 to the 11, and we can compare the composition of the rotation curves from what we see in the observations to what we actually have in the simulation. So this is what I'm showing you here. This is one galaxy that we observe, this is a fairly massive disk that has a halo mass that we measure to be of the order of 10 to the 12. And this is the rotation curve decomposition that we can derive. So as you can see, the galaxy, the dynamics of the system is dominated by the stars up to of the order of 25 kpc, and then dark matter starts to kick in at around this radius. And this is a very important difference with respect to similar galaxies that have, you know, similar flat rotation curves and have similar stellar masses in the simulations. But their decomposition is very different from what we see here. In particular, if you look at Eagle, the galaxy, this galaxy starts to be dark matter dominated within the effective radius. So within 10 kpc. And in TNG, the situation is a bit better, but still the dark matter starts to dominate the dynamics of this system at around 10 kpc, whereas in the observation, it was at much farther radii. So this is obviously, this happens not only for this galaxy, but this is a systematic issue that we see in the simulations. And you can look at only at the right panel of this diagram. So here I'm showing the stellar over dynamical mass ratio as a function of radius. So basically what I'm probing is I'm dividing the if you want the yellow curve by the rotation curve, by the black points, and this allows me to probe the ratio, you know, the ratio of mass in stars and dynamical mass as a function, as across the rotation curve, right? So as a function of radius. And if this is larger than 0.5, obviously this means that stars dominate the dynamics. If it is lower than 0.5, this means that dark matter dominates the dynamics. And as you can see, if you select the massive disks in SPARC, that are the red points and the red band, you can see that the stars dominate the dynamics of disks up to of the order 2 effective radii, whereas in the simulations, dark matter kicks in and starts to dominate the dynamics within the effective radius. So these are massive disks. These are the most massive disks, both in the simulations and in the observations. And we can see that in the simulations, disks tend to be too dark matter dominated everywhere, both in a global sense, meaning that they have a lower than average stellar over halo mass ratio, but also in the local sense, because their dynamics is everywhere too much dominated by dark matter. And so the conclusions is that we now have a pretty good understanding of the stellar to halo mass relation from individual measurements of halo masses in spiral galaxies and in disk galaxies, and in the elliptical galaxies, and we have evidence that the stellar to halo mass relation tends to be linear for spirals, while it tends to have a clear turnover at masses of the order of the Milky Way only for ellipticals and lenticulars. And so typically at these high masses, ellipticals tend to live in much more massive halos than spirals. And this, we call it failed feedback problem, just because we are proposing that if the stellar mass function as a turnover as a consequence of AGN feedback, then this might mean that the spirals have, for some reason, AGN feedback in these systems have not kicked in and have not had time to quench them completely. And we also saw that in the simulations, there are still some issues in the sense that disks tend to be too dark matter dominated with respect to what we observe. And I stop here.
Well, thank you really much, Lorenzo. It was really interesting. I really liked it. So is there any question? I see Andrea having one. So please go ahead.
Yeah, it's actually a comment and a question, Lorenzo. So the comment is about the comparison with the simulations. On one hand, it makes sense when you if you go back a few slides that you show the stop here. So okay, here it makes sense that you see that the TNG galaxies are they have a higher fraction, so they have moved more to the SPARC data, because you know that in TNG at high masses the feedback is
Yeah.
Also, we saw it also in a paper with James Angtopo here on the Green Valley galaxies. However, my question is more observationally oriented. In the sample of early type that you used, did you consider to use the massive survey that also overlaps with Atlas 3D on the high mass end? Because I know that they have good kinematic data and they are massive. So I was wondering if you consider this or if you excluded it for reasons that I don't know.
Yeah, so on the first on the first part on the comment, yeah, absolutely. So this is, I'm not claiming to be the first one to see any difference in this. It's very important that you point this out, meaning that there are different groups that are starting to see differences, both in the simulations, as you say, but also in the disks, right? In the fact that the disks tend to have, both in TNG and in Eagle, higher F star than with respect to the average. I think this is it's very important to point out that I'm absolutely not the first one to say that this is the case. On the observational side, no, I've not considered the massive the sample from the massive survey, just because I was doing an analysis on a sample that was, I chose slugs just because it was there and was ready, and I thought it was nice, and I just applied as a method that worked quite well on that. But definitely there are many other different probes of the dynamics and on the halo mass of massive early types. And I think they all kind of agree in saying that the ellipticals and the early types tend to follow the expectations of abundance matching. And I think this is the key, right? So both any probes that you can think of, kinematics of global cluster, planetary nebulae, X-rays, lensing, they are all going to tell you that the early types do fall within the range expected by abundance matching. So I didn't find, I didn't think of using all of the other samples yet, but for from the papers that I've seen, I think they all tend to agree with this picture, I think.
Thanks.
No, thank you. Thanks.
So, Nacho?
Hi, Lorenzo.
Hi.
Nice talk.
Thanks.
I just want to make a comment and then a question. So in relation to my comment is that the idea that you are pushing that there is a very different halo depending on the morphological type is also suggested by when you look at the number of satellites. For example, if you fix the stellar mass, so this has been published 5 years ago. So when you fix the stellar mass, you see that the elliptical galaxies have a factor of 4 more satellites than spiral galaxies of the same stellar mass. So when we publish that result, our interpretation is slightly different to yours in the sense that what we think is going on is that because elliptical galaxies form early on, or at least the stellar populations are very old, and they have also removed the gas quickly. So the difference are that in our interpretation, the difference were more on the line that you were not forming more stars over the years. Okay, so somehow the dark matter halos containing elliptical galaxies was more inefficient at forming stars. So the emphasis was put on the availability of the galaxy to form stars more than on the feedback issue. So so I would like to know your opinion on that. So it's a different perspective of the same phenomenon, but instead of putting the focus on the feedback from the black hole, let's say the supermassive black hole, is in the lack of gas you have for forming new stars over the years. What do you think about that?
Yeah, absolutely. So thanks for the comment. This is absolutely this is all great, right? In the sense that what we are seeing as well is perfectly compatible with what you say, in the sense that really what we are seeing is a difference in the stellar to halo mass relation of spirals and ellipticals. And effectively what this means is that the quenching of spirals and elliptical must have been different, which is probably something not very new, right, in some sense. And so our interpretation then in terms of AGN feedback is obviously kind of stretched, if you want, right? Is a bit possibly even far-fetched, in the sense that we were trying to when we started interpreting this in terms of AGN feedback, we were trying to go back to the kind of general consensus that this turnover is caused by AGN feedback. I think many people in the community have this in mind. And so we were trying to, okay, let's assume that this is the case. Then if this is the case, then this probably implies that the spirals must not have had a significant AGN feedback, right? But this is not what we see, right? What we see is something that is perfectly compatible with what you say. And let me tell you, there are also other interpretations that might be, there are other processes that might be very important that cause this drop off here for the ellipticals. For instance, merger history, right? It might be that if you fix a stellar mass, a galaxy that is elliptical happens to have lived in a halo that had a merger history that was more violent, and so star formation might have quenched as a consequence of mergers. Instead, a galaxy of a similar stellar mass that is spiral has been living in a halo that has not merged a lot, so whose history was much more quiet. And so the star formation there has not quenched, and galaxy could form stars at about constant rate for its entire lifetime, right? This could be another way of interpreting this what we observe here that does not invoke AGN feedback at all. So what I did here was just to point towards what would be a consequence if you think that AGN feedback is doing this for ellipticals. Then this must mean that AGN feedback does not do does not quench spirals, right? So I welcome all of the other interpretations as the one that you said, because this is we don't have yet a complete a way to disentangle these things. I think we would need to go into, for instance, probing the AGNs in spirals in high mass disks. This would be a way possibly to disentangle if this interpretation is correct or is not at all.
Well, thank you very much. Jorge.
Okay, thanks for the talk, for the nice talk.
Yeah, thank you.
Could it be that the problem is in the way you compute the halo masses of the massive spirals? In a sense, could you tell us how do you derive the masses from the rotation curves? Because if I get it properly, the Navrov and Y profiles have infinite mass. So if you keep integrating forever, you get something. So you have to decide what is the size of the halo, and so the actual mass. And so somehow you are relying on this relation between concentration and mass. And what if it doesn't work?
So what I'm doing here is actually comparing, a virial mass, right? A halo. The mass, the virial mass of the NFW halo, which would be defined as 2 times the over density, 2 times more dense than the average density of the universe, right? And the critical density of the universe. So this is where I define the threshold mass. As you say, NFW is a profile that integrates to infinity. So I stop it at the virial where the virial mass would be defined, so at the virial radius, if you want. And this is consistent with the gray bar, with the gray area, right? With the abundance matching determination. This is basically what they probe as well, right? They probe the relation between stellar mass to virial mass in the local universe. But as you say, it is very important on how I perform the fit, right? So the inference on the total virial mass depends on the extrapolation of this purple curve to the virial radius. So in this galaxy in particular, if it has a virial mass of the order of 10 to the 12, it would have a virial radius of about 200 kpc. So this would mean that I'm extrapolating the purple curve to 200 kpc, and I'm integrating up to there, right? So I have no data after 50 or 60 kpc. So how do I do this extrapolation? This extrapolation just follows the NFW profile. And the mass that you derive in the end is very sensitive on how you make this extrapolation. However, in our lambda CDN cosmology, I don't think there are any other ways to make halos that does not follow an NFW, meaning Meaning this would be basically the if you want, the most conservative assumptions, right? We know that that in lambda CDM halos have a slope of about r to the minus 3 to the in the outskirts, or even steeper than that. And so if you assume r to the minus 3 is basically the most conservative assumption, meaning that you have the higher halo mass that it can have. And so this is basically what I'm doing. Meaning what I'm trying to say is if I were to use like an Einasto profile to fit for the rotation curves, I would have a lower halo mass. And so the discrepancy here would be larger. So using an NFW to fit in these galaxies is actually brings the points, if you want, as close as they can be to the gray band.
Okay, so thank you.
Yeah. But let me just say that what kind of halo model you use is very important, and if you use a model that has a core, for instance, in the inner part, the fit that you end up having is slightly different. However, we see that at the high mass end, this doesn't account. This cannot account for such a difference that we see here. So basically, no matter what halo profile you use, you will kind of always see that these galaxies are overshooting the abundance matching expectation.
Okay, thank you.
Mark?
Yes, thanks for this very interesting talk.
Thank you.
I kind of recall that about 20 years ago, cosmological simulations could not make disks. And a big thing was when somebody finally made a disk. It was kind of a smaller than normal disks. There were several discrepancies, but at least there were disks. So the general violence, the general gravitational violence was controlled in a way, perhaps because we changed to a lambda CDM cosmology, and I'm not sure why, but eventually disks started to appear. Now, I was very fascinated with your plot comparing with the two of the latest simulations, in which those disks are really not quite up there in comparison with observations. And I wanted to ask, what happened to these disks that are not massive enough? Is it that they never formed, or is it that they formed and they merged into ellipticals?
So you mean if there could be, let's say, at higher redshift or in a different stage of the simulation, something that looks like this, right?
Yes.
That is your question. Yeah, I am not sure actually. This is a very simple comparison that we did, and probably people that have a deeper knowledge that we have on the simulations would be welcome to have a deeper look at this. But my impression is that they don't have, is that they never had disks that were so big and that had such a high stellar over halo mass ratio. But this might be my impression. And just to add something on the historical note that you said, I think one of the important points in order to form disks 20 years ago was the addition of feedback, right? Especially stellar feedback was a critical ingredient in order to form disks, because one of the problems that you had is that you kept cooling gas at the center, and you couldn't form a nice extended disk because you had no way of redistributing angular momentum around, and so you formed stars out of gas material that had too low angular momentum, and so you had no way of redistributing it in a large extended disk. And in doing this, stellar feedback was crucial. When you add feedback, now feedback is able to kind of give you a redistribution of angular momentum, and so it enables you to form these nice extended disks. Now, this problem here at the high mass end, I think, is very important because if you shut off completely AGN feedback in these simulations, probably you will be able to make galaxies that have this high stellar to halo mass ratios, but I think you will be having huge bulges because you will not be able to have redistributed angular momentum efficiently in the center. So this is my kind of speculation of something that I've seen in going around with some literature in the simulations. And I think this should be addressed a bit more, right? Because these massive disks, we have good data right now, and we kind of know these things. We kind of start to know this, and we know how many of these massive disks are around there. And so I think it would be interesting from the simulations point of view to have a look at what happens, for instance, if you don't have AGN feedback at all, if you can't form any of these things, and how. It would be very cool.
If I can add a quick question in response to what we just said. So you're saying you believe that it is internal and not quite so much an external. So the way the gas comes into the disk and the dissipation processes are well understood, so that we're not over dissipating the dynamics of the incoming gas.
Yeah, what I'm trying to say is, I think these massive disks might be a very nice test case, right, for precisely understanding this in the simulations. I have the impression that the simulations have focused a lot on a slightly lower mass scale, which is around the mass of the Milky Way, for a very large number of very good reasons. But I think I would be I would like some of these simulations also to have a look at what happens at the slightly higher mass end, because I think that we might see something that we do not expect, right? We might see that, at least in the observations, we see that the star to halo mass relation keeps growing. And I suspect that this is not reproduced very well in the simulations at the moment.
Thanks.
Okay, thank you very much. So if the two last questions can be really quick, that would be great. So the first one will be IG, and then we will finish by Ariana.
Okay, just very quickly. So excellent talk, actually, Lorenzo. It was also very pedagogical, so it was very nice.
Thanks.
So I must say that going back to the point that Jorge mentioned, I mean, the thing is you're basically explaining all this in terms of a variation in feedback in early types and late types, which I really believe that there has to be something there. But there's also this issue that is in the estimation of the halo masses, you're enforcing exactly the same prior on the concentration virial mass relation for early types and late types. Now, one possible hypothesis is that because of the formation history has been different, maybe the concentrations are different. So one option is that the concentrations of late types are lower, automatically the halo mass will be lower, and perhaps you might be able to reconcile these two better. So have you thought about this prior?
So I've explored varying the prior. I've taken a concentration mass relation, then I've taken a prior 1 sigma above, then 1 sigma below, then flat, then steeper. So I've tried doing all of this in both samples, and I've always seen this difference. So this tells me that within the standard understanding of the concentration mass relation that we have from and body, I think we cannot explain it with simply a difference in concentration. This is what I've seen given my tests. But I think there might be some leverage there, right? If we allow, for instance, the spirals to have a significantly different CM relation than ellipticals, then it might be. Yeah.
Okay, great. Thank you.
Yeah, thanks.
Okay, so Ariana.
Okay. Yeah, I'm using Ariana's because my hand up.
Both.
Very nice talk. So I'll be
Thanks.
quick. I was just wondering, with the different interpretations that are possible, have you looked at whether there's a difference in the halo mass stellar mass relation at this high mass end for the different morphologies? The black hole mass, sorry, the black hole mass stellar mass relation, because this could show up if it's caused by black.
Absolutely. So I think this is one of the ways to test this kind of speculation that I have, and we are actually doing this at the moment with some collaborations of mine, and we don't see a clear difference as we would expect. This is something that I was very puzzled, and I don't know what it means, and I kind of believe the measurements that we have, because we have galaxies with halo masses that are estimated from rotation curves or from globular cluster dynamics, and we have black hole masses that are dynamically measured, either with the usual ways, right, kinematics of gas or stars. So I kind of believe all of these measurements, and I don't see a clear difference between the black hole masses spirals and ellipticals, and this puzzled me. I don't know what it means. I don't know if it is still compatible with the picture that I've shown here. Maybe it is not, but I think this is one way to test it. Absolutely, from the observational point of view.
Interesting. Thanks.
Yeah, thanks.
So if I may finish with the last question, it will be for, have you tried to do the same thing, but instead of taking the full mass of the halo, to try to fix at the scale length of the halo, for example, or something like that, just to see at a very specific distances if you have the same kind of discrepancies?
Yeah, no, I haven't done it actually. The only thing I've looked at a fixed scale length was basically this, right? So this is something that we can do for all galaxies and for spirals and ellipticals. From what I've seen making this diagram also for ellipticals, it doesn't look like there is a huge difference, but there might be. It might be that the ellipticals are slightly below, and I didn't see it very well. So it might be interesting to see. At least there is a global discrepancy, and it might be even across radius. It could be.
Okay.
Good point.
Okay. So thank you very much.
Thank you.
So that's all. Thanks again to Lorenzo for his really nice presentation. And let's see us soon for the next seminar. Well, thank you again.